All right, hello and welcome to this tutorial. If you have one of these errors, lots of negative Jacobians detected, error termination, you've come to the right video. Let's get started with what really is even a negative Jacobian. So the Jacobian takes the locations of each node of each element, and using those locations, it calculates the determinant, which is kind of a corollary of the volume. And so I actually had ChatGPT write me a little script to demonstrate this. So imagine this is one tet4 element. It's a tetrahedron that has four nodes. And right now, its determinant is 1. You can see it's just the determinant of the different locations of each node. All right. And so with every click, its determinant is going to get smaller as node 4 moves down. So notice, okay, we're at 1/2. And so it is getting really shallow here. What happens if it goes all the way 0? Then we have a negative volume. We can't really have a negative volume. That doesn't make sense. And so if your finite element code is calculating negative volume anywhere in your model, then that's an issue. So that's what a negative Jacobian is. 0 also counts as a Jacobian error. So if you have 0 volume in an element, then it's not really an element anymore. So that's what could be causing your negative Jacobian errors. So what can we do? The FEBio manual has some ideas for us. So here in febio.org, the user manual, if we come to common issues, inverted elements. All right. And it gives a little blurb, and then we have 5 different ideas for what might have caused that. So first off, material instability. This has to do with the math of how we define our materials. So FEBio is built for hyperelastic models. Elastic would be linear and pretty straightforward. However, hyperelastic gets pretty complicated. I mean, look at this math of the Mooney-Rivlin model. Um, that's a lot, right? These come from experimental tests. And so what if your hyperelastic model is only defined up to a certain strain? If you go beyond that strain, then maybe weird stuff can happen, right? Or what if your model is defined up to very large strains? However, sometime in some models, stiffness actually decreases. And so if you are pushing harder and harder with each time step in your model, and the material gets softer and softer, then that's going to cause some real numerical issues. And so potentially I would recommend potentially just changing to a different material model that is defined at the strain you need, or maybe you are overstraining it. So double check both of those. Are the loads correct? Are the materials correct? All right, the next thing on this list is time step too large. So if I open up the results, okay, here we go. So we see that FEBio here, I'll make the timeline bigger. FEBio will do smaller time steps when it runs into issues. It will run into an issue, and then if it can't solve, it will cut back to a smaller time step. And so you'll see, okay, we really ran into issues right at time equals 1, right at 1.1, 1.75 about, and then we must have run into more issues at this 1.986 when it ended. And so what we can do is we can actually say, okay, we know it's going to run into issues here, so we can just pre-cut our time step back. So if you'll notice, it started out with a pretty small time step at the very beginning, and then the time step got bigger up into about here, where from here until it runs into issues again, it's kind of just jumping along at this same time step. So this is our DT max, and we can edit that right here. This is our FEB file. Oh, so this is in steps. We come to the step in question, then, okay, time steps, step size. We can change the default step size, minimum step size, maximum step size. So if you're running into issues, maybe you should decrease your max step size and maybe even decrease your min step size, because if it tries the minimum step size and it still doesn't work, then it will quit, right? You can also set up a load curve to these. So actually we can come up to the curve editor. Again, I'm in my FEB file, come to the curve editor, and I'm going to say, okay, in step 1, time stepper. Okay, I'm going to make a new load controller for my DT min or DT max, so that rather than having all these different time steps, right? If you set your DT max to be very small, then you're going to have so many time steps throughout your whole model, and that's going to take a long time to solve, and it's going to make your XPlot file super big. And so you can set up a load curve to, maybe I want my DT max to be 0.1, and then at a certain spot, make it smaller, and then make it increase again. So that's one thing we can do if our time step is too large. All right, if our elements are too distorted, what can we do, and what does that even mean? Well, if I bring this back and run it again, you can imagine this is a very ideal element. Let's say our meshing started out kind of squashed like this, then you can imagine that it's more susceptible to inverting, right? I mean, sometimes you might have an element with a Jacobian like this where it is so small, very likely that it will invert with any change from there. So we can come to our FEB file, and how do we check for that? We come to the mesh inspector, the little investigator guy, detective, then we can see, okay, if we look at the Jacobian, this will highlight where it is high and where it is low. And so we're looking for all of these really blue areas. These might be potential areas of interest to alter. So there you go. Our next thing is, are our shells too thick? So if you have a shell element, I actually have 2 shells right here. These are modeled as 2-dimensional sheets that are draped. And then in the software, when it runs, it will add a thickness to it. And so you can imagine if this is the sheet that I define, and then it adds a thickness based on those elements inside, that some of these elements are going to crisscross. And that is not good. That will throw a negative Jacobian error. And so if you have shell elements in your model, maybe consider reducing the thickness or simply modeling it as solid elements, or you can remesh to try to get it to reform. All right, and then our last one here is rigid body modes. So if this one's kind of weird, if I have, for example, a part that FEBio thinks is supposed to stretch, undergo some sort of deformation, or have some internal stress, and it doesn't, it just simply like moves all together without getting stretched or pulled at all, then there's no like single solution. And so that's going to throw an error. It has to have some sort of constraint on it, or else you'll have this negative Jacobian error. All right, in my case, however, it's a combination really of the element quality. Some of these are kind of thin to start out with. You can see these guys are very thin and very squashed. And so that makes these very sensitive. And then the material can be kind of soft, And lastly, my time step can be kind of large sometimes. So it's kind of this combination of things. And I've found that simply editing the contact parameters can really have a huge impact on whether I get these negative Jacobians or not. Because if I have a high penalty, then as the contact surfaces come close to each other and penetrate a little bit, then it will multiply force by the contact penalty by the contact penetration. So if I penetrate a little bit and have a really high penetration factor, then it's going to push really hard, and that might invert my elements, causing the negative Jacobians. And so I want to just edit my contact parameters because I know that's tricky anyway. But look at how many contact interfaces I have. I mean, each facet joint at every level has a contact interface. And so I need some help finding where that might be. So if I come to the XBlot file, then there are some tools that can help. I'm going to hit M so that the mesh is hidden and it just works a little nicer. All right. If I come here and look at relative volume, then we can kind of see, okay, it's all uniform at this time step, but if I come to the last time step and zoom in, then we can see, okay, the bones may have the same volume as before because they're rigid, but we can see where the relative volume is less. And so places where we have a very low relative volume are potential places where I might be hunting for negative Jacobians and trying to alter parameters there. In this case, it looks like every joint is going to be having some of these issues. I can try to slice through and take a look. So if I look at my plane cut, I'm going to make this Y normal and not X. All right. And so I can try to look for contact penetration here, which is frequently associated with these very high forces and negative Jacobians. Oh, so there's some penetration here, which may be causing these negative Jacobians. And so this is a good place to start. Edit contact parameters to resolve the negative Jacobian issue. I can also delete the plane cut. It will go away. And if I click here, the color map will go away. Okay. I can still here do the mesh inspector and look for elements that may have a Jacobian between 0 and something very small, like 0.001. So if I select all those, then I'm going to include only my hex 8 elements, which is my facet joints and my intervertebral discs. So, okay, here we go. 0.004 to I'm going to say 0.009. And I'm going to select all those. Okay, so here are the places where the Jacobian is very small. I'm not particularly worried about my intervertebral discs. They have worked pretty well for me in the past. So mostly I'm concerned about, you can see these highlighted portions right here in this facet joint, in this facet joint, in this facet joint, and in this facet joint. So those 4 are where I'm going to start to sleuth out where my contact might be having issues. Oh, and here's another one right here in this facet joint. So there are 5. Oh, and another 6 right here. Kind of blends in with the orange. And if this isn't working for you, then there is one last-ditch effort where you can actually get FEBio to tell you where the negative Jacobians are happening. So let's do that super fast. To do that, we actually have to run FEBio from the command line. So if I type CMD, and then I'm going to navigate to my desktop where the file is. Now I'm going to type FEBio 4 to start FEBio. And okay, FEBio is open. So now what I'm going to do is I'm going to type set space output underscore negative underscore Jacobians, plural, space 1. There we go. So output negative Jacobians equals 1. And now that that is turned on, I can say run space and then my file name, whatever it is, .feb, and then it will run. And in the log file, it will tell you which elements are inverted at every time step. And so that will show you where you're having these issues. I'll likely make another video on running FEBio from the command line, and there's some setup that goes along with that. But there you have it. That's the video. I really hope this helps, and I wish you all the very best. Thank you so much.